Dear students, welcome to this maths class. Confidence and hard work is the best medicine to kill the disease called failure. It will make you a successful person. These are the words of APJ Abdul Kalam. So children, you should study regularly and you should work hard. If you work hard, you will succeed. So in this section, we will study rational and irrational numbers from a different point of view. Here we will study the decimal expansion of real numbers and see whether we can use the expansions to distinguish between rational and irrational numbers. In fact, seen by a decimal expansion of a number, we can know whether the number is rational or irrational. Since we are more familiar with the rational numbers, so first we will consider some decimal expansion of rational numbers. For example, 10 by 3, 7 by 8, 1 by 7. Let us consider these three examples. The decimal expansion of first number 10 by 3 is 10 divided by 3. Here the divisor is 3. 3 3s are 9. Remainder 1. 1 is smaller than 3. You put decimal point and you can continue the division process. When you are putting decimal point here, you can put 0 here. So now the number is 10. In 10, how many 3s are there? Again, 3 3s are 9. Remainder 1. Again, you can continue the process if you put one more 0 here. Now it is 10. There are 3 3s are 9. Remainder 1. So again you can put 0. Then 3 3s are 9. Remainder 1. It's not ending, it is continue like this. The division process you can continue this way, you are getting 3.33 etc. Now look at the next number 7 by 8. 7 divided by 8. 7 is smaller than 8, so we cannot continue the division process. So you have to put decimal point, then write 0 on the right side of this number. So 70. So 70 is it's more than 8, so we can divide this. So 70 by 8 is 8 8s are 64. Remainder 0 minus 4 is not possible, so you have to borrow from here. So 10 minus 4, that is 6. Again, you can continue this 60. So 7 8s are 56. Remainder 10 minus 6, 4. Put one more 0, now 40. 40, how many 8s are there? 5 8s are 40. The remainder 0. We got the remainder 0. So we stop the division process. When you are getting the remainder 0, we are stopping the division process. So the quotient of this decimal expansion of 7 by 8 is 0.875. The next number is 1 by 7. Here 1 is smaller than 7, so you have to 0 point. Now it will be 10. In 10, how many 7s are there? 1 7 is 7. Remainder 3. Now put 0. Now it is 30. In 30, how many sevens are there? 4 sevens are 28. Remainder 10 minus 8, 2. Again, can put 0, 20. 20 divided by 7. 2 sevens are 40. Remainder 6. Now 60. In 60, how many sevens are there? 8 sevens are 56. Remainder 4. Now it is 40. In 40, how many sevens are there? 5. 5 sevens are 35. Remainder 5. Again, you can continue the division process. Now it is 50. In 50, how many sevens are there? 7 sevens are 49. Remainder 10 minus 9, 1. Again, you can continue this process. Now, if you put 0, it will be 10. In 10, how many sevens are? 1 7 is 7. 1 7 is 7. Again, remainder you will get 3. So, children, if you continue like this, you can see that the remainder is not getting 0. It's continuing like this. That time the quotient also repeating like this. 1, 4, 2, 8, 5, 7, 1, etc. So from these examples, when you observe these reminders, in the first case, the reminder is repeating. The one is repeating always. The reminder is 1 only in all cases. It is repeating. Now when one is repeating, the reminder is repeating, the same time you can see the quotient also, some digits are repeating. And in the second case, you got the reminder is 0. When you get after a few steps, you get the reminder as 0. So we complete the division process, or the quotient is ending after after some steps. And the third case, the remainder is repeating. You can see the remainder first 3, then 2, then 6, 4, 5, 1, etc. The quotient also repeating like that. Quotient, the digits, some block of digits are repeating. You can see that 1, 4, 2, 8, 5, 7. Again it's coming 1. Next 4, 2, like that it's going. So from these three examples, you will understand two things. So the first one is the remainder either becomes 0 after a certain stage or start repeating themselves. And the number of entries in the repeating string of reminders is less than the divisor. Look at the example 10 by 3. Here the divisor is 3. The reminders are 1. 1 is smaller than 3. And look at the example 1 by 7. There the reminders are 3, 2, 6, 4, 5, etc. So these numbers are smaller than 7. The divisor is 7. And the second one is, if the remainders repeat, then we get a repeating block of digits in the quotient. Look at the first case and the last case. Remainders are repeating. That time we are getting the repeating block of digits in the quotient. In 10 by 3, 3 repeats in the quotient. And for 1 by 7, we get the repeating block 1, 4, 2, 8, 5, 7 in the quotient. So it is true for all rationals of the P by Q. On division of P by Q, two main things happen. Either the remainder becomes 0 or never becomes 0. And we get a repeating string of reminders. Let us look at each case separately. The case 1, first case. Look at this example. The remainder becomes 0. In the first case, the remainder becomes 0. In the example 7 by 8, the remainder becomes 0 after some steps. And the decimal expansion of 7 by 8 is 0.875. If you take another example like 1 by 2, we know the decimal expansion of 1 by 2 is equal to 0.5. And decimal expansion of 36 by 100, that is equal to 0.36. In these all examples, you can see that the decimal expansion terminates or ends after the finite number of steps. After a finite number of steps. Decimal expansion of 7 by 8 and decimal expansion of 1 by 2 and the decimal expansion of 36 by 100. These all are terminates or ends after a finite number of steps. So such decimal expansions are called terminating decimal expansion. Terminating. Terminating decimal expansion. The decimal expansion of these numbers are terminating or ends. Terminate means ends after a certain steps. So such numbers are called terminating decimal expansion. So in the second case, the remainder never becomes 0. In the first case, we see that the remainder becomes 0 after a certain stage. In the second case, in the example 10 by 3 and 1 by 7, you can see that the remainders never become 0. The remainder repeats after a certain stage. Here the remainders are 1, 1, 1, etc. Here the remainders are 3, 2, 6, 4, 5, etc. At the same time, we can say that the decimal expansion of these numbers are repeating. The block of digits are repeating in the quotient. Here 3 is repeating. Here 1, 4, 2, 8, 5, 7, etc. That means the block of digits are repeating. So when the remainders are repeating and at the same time it forcing to repeat that quotient also, and some block of digits are repeating in the quotient. So the decimal expansion of such numbers are called non-terminating recurring. Non-terminating recurring. Recurring means repeating. Non-terminating, repeating. That means non-terminating means not ending. The decimal expansion is not ending, but it is repeating. So this type of decimal expansion is known as non-terminating recurring or non-terminating repeating. And thus, the decimal expansion of 10 by 3, the number 3 is repeating. So it is written, you can write it as 3.3 is repeating. So you can write 3.3 bar. The bar above the digits indicates the block of digit that repeats. And in the decimal expansion of 1 by 7, here the block of digits, that is 1, 4, 2, 8, 5, 7, a block of digit is repeating. So we can write it as 0.14285 7 bar. The bar indicates the block of digits that repeats. So the block of digits are repeating, so you should draw the bar above that digits. And third one, the decimal expansion of 1 by 3, 0.33, etc. Here 3 is repeating, so we can write 0.3 bar. That means 3 is repeating. Here the block of digits are repeating. And the same way you can write 3.257, 57, etc. So this is also a non-terminating, repeating or non-terminating recurring decimal expansion. Here you can see that only 2 digits are repeating. 2, then 5757 is repeating. 2 digits only repeating. So we can write it as 3.257 bar. The bar is only for this 5 and 7 because that 2 digits only repeating. So from these all examples gives us non-terminating recurring decimal expansions or non-terminating repeating decimal expansions. So thus we can see that the decimal expansion of rational numbers have two choices. Either they are terminating or non-terminating repeating. That means the decimal expansion of rational numbers are terminating or non-terminating recurring. Here we saw that the decimal expansion of rational number is non-terminating recurring or repeating. Or otherwise we see that the decimal expansion is terminating. Suppose a number whose decimal expansion is terminating or non-terminating recurring, can you conclude that it's a rational number? For example, if the decimal expansion is given for you like this, suppose this, in this example, this is a decimal expansion of a number. Can you say that this number is a rational or not? Rational number means we know that the number which can be written in the form of P by Q, where P and Q are integers and Q not equal to 0. So can you write this number as P by Q form? Let us check it. Consider these examples. Show that 2.125 is a rational number. When you observe these two examples, you can see they are terminating decimal expansion because after a finite step, decimal expansion is ends. And here also it's a terminating decimal, it's not repeating. So here 2.125 we can write it. Now it is a decimal form. You can change this decimal form into fraction form. Because it's a terminating decimal expansion, we are able to write 2.125, we can write it as 2125 by 1000. Now it is in the form of a P by Q, where P and Q are integers and Q not equal to 0. So we can say that it's a rational number. Look at the next one. This number, here there are 5 decimal places. So when you change the decimal into fraction form, it will be 14,273 by so that's also we can write it in the form of P by Q. So we can say it's also a rational number. Then show that 0.333 etc. Show that 0.333 etc. is a rational number. That means you want to write this number as in the form of P by Q. Can you write this number as in the form of P by Q? You cannot write directly like this because it's here the number 3 is repeating. It's a non-terminating recurring decimal expansion. So directly we cannot write like this. For that, we have to consider this number. Let x be a rational number. So let x is equal to 0.333 etc. That we can write it as 0.3 bar. Is it? Now multiply 10 on both sides. Why means here one digit only repeating. If there are only one digit is repeating, you have to multiply by 10. If there are two digits are repeating, you should multiply by 100. If three digits are repeating, you should multiply by 1000. Here only one digit is repeating, that is 3 only repeating. So multiply both sides by 10. Then it will be 10 into x, 10x is equal to 10 into 3.33 etc. 10 into 0.33 etc. So 10 into x, 10x is equal to 10 into this. So one decimal place will move to the right. So it will be 3.333 etc. you will get. Now we can write 10x. Here you can take this as equation 1. This you can take it as equation 2. Subtract equation 1 from equation 2. Or you can write this way 10x, we can 3.33 etc. This number you can split, you can write this way 3 plus 0.333 etc. You can split this number and you are able to 3 plus 0.33, that will be equal to 3.33. Otherwise, you subtract equation 1 from equation 2. So we will get 10x equal to 3. We already taken x is equal, we know this value we will take as x. 0.33 we taken as x. So instead of that you can substitute that x. So 10x plus equal to 3 plus x. Now you can solve, you take this x to or transpose this number to the side, then it will be 10x minus x. Positive x will be negative x, that is equal to 3. 10x minus x is equal to 9x, which is equal to 3. So x is equal to 3 by 9. The 9 is a multiplication that is going to that side, so it will be a division. So x is equal to 1 by 3. We got x is equal to 1 by 3. Now 1 by 3 is in the form of p by q. Here we know what is the value of x. Here x is equal to 0.333 etc. So now we are getting 0.333 etc. is equal to 1 by 3. So the decimal expansion of this 1 by 3 is, that means the non-terminating repeating decimal expansion, that we write it in the form of p by q. So we can say that it's a rational number. Let us see one more example. Show that 5.2 bar can be expressed in the form p by q, where p and q are integers and q not equal to 0. That means show that this number is a rational number. So we know that 5.2 bar, that will be equal to, we can write it as 5 point. The bar indicates that digit is repeating. So 2.222 etc. Now let us take, let x is equal to, x be a rational number. So x is equal to 5.222 etc. Give it as equation 1. Here we can see that only one number is or one digit is repeating. So we want to multiply by 10. So multiply both sides by 10. So 10 into x, 10x equal to 5.222 etc. into 10. So one decimal point will move one place to the right. So it will be 52.222 etc. Give it as equation 2. Now we can subtract equation 1 from equation 2, or we can split this number. So if we subtract equation 1 from equation 2, it will be 10x minus x. It will be like this. Equation 1 subtracting from equation 2. So equation 1 is x equal to 5.22 etc. We are subtracting equation 1 from equation 2. So we will get here 10x minus x is 9x, which is equal to 52.22 etc. minus 5.222. Here 2 minus 2 0, 2 minus 2 0, 2 minus 2 0, and decimal point. Then 2 minus 5, that is not possible, so you have to borrow from here. So here 4, here 12. So 12 minus 5 is 7, 4 minus 0, 4. So we got 9x is equal to 47. So x is equal to 47 divided by 9. 47 divided by 9. It is in the form of p by q, where p and q are integers and q not equal to 0. So x means, what is x? 5.22. We got 5.222 etc. is equal to 47 by 9. So we are able to express 5.2 bar in the form of p by q. So it is a rational number. See the next question. Show that 1.27 bar can be expressed in the form p by q. We know that 1.27 bar, which is equal to 1 point, here bar is indicating above these two digits. So bar indicates these two digits are repeating. That means 1.2727 etc. So let us take x is equal to 1.2727 etc. Here we see that two digits are repeating. So we want to multiply by which number? We want to multiply by 100. If you have only one digit is repeating, then you multiply by 10. If there are two digits are repeating, so you should multiply by 100. If there are three digits, you should multiply by 1000. So let us take this as equation 1 and multiply both sides by 100 in both sides. So it will be 100 into x equal to 100 into 1.2727 etc. So which is equal to 100x equal to 100 into 1.2727 etc. means there are two zeros are there, so the decimal place will move two places to the right. So it will be 127.2727 etc. Give it as equation 2. Now subtract equation 1 from equation 2. So subtract equation 1, that is 1.2727 etc. When you subtract these, you will get 100x minus x is equal to 100 minus 1. that is equal to 99x is equal to, here we get, after the decimal place you will get 0. 2 minus 2 0, 7 minus 7 0, all these values will be 0. And 7 minus 1, 6, 2 minus 0, 2, 1 minus 0, 1. So 99x is equal to 126. Therefore, x is equal to 126 divided by 99. If there is common factor, you can take it or you can write it in the lowest form. I think there will be 3 is the common factor, so it will be 42 divided by 33. So x is equal to 42 divided by 33. It's in the form of p by q, where p and q are integers and q not equal to 0. So we can say that the number 2.27 can be written in the form of p by q. So it's a rational number. And this question, show that 0.235 bar. Bar indicates only the digits 3 and 5. That means 0.235 bar is equal to 0.235, the digit 3 and 5 only repeating, because that bar indicates only these two about these two numbers. So 0.23535, etc. Let us take x is equal to 0.23535, etc. Only these two digits are repeating. So here two digits are only repeating, so you should multiply by 100 in both sides. So it will be 100 into x is 100x, which is equal to 100 into 2.3535, etc. So the decimal point move 2 places to the right, so you get 23.5353, etc. Take this as equation 1, this is equation. Now subtract equation 1 from equation 2. So it will be x is equal to 0.23535, etc. When you are subtracting, 100x minus x is 99x, which is equal to, here you can see 3 by 3, 0, 5 by 5 minus 5, 0, 3 minus 3, 0, 5 minus 2, 3. 3 minus 0, 3, 2 minus 0, 2. So 99x is equal to 23.3. Therefore, x is equal to 23.3 divided by 99. It is in the form of p by q, but p is not an integer. It's a decimal number. So you have to change it to the fraction form. So what you have to do, you have to change the decimal in the fraction form. So for that you should multiply the numerator and denominator by 10. One decimal point is here, so you should multiply numerator and the denominator by 10. Then it will be 233 by 990. So now it is in the form of p by q, where p and q are integers. So from these all examples, we understood that every number with a non-terminating recurring decimal expansion is expressed in the form p by q. That means a number whose decimal expansion is non-terminating recurring is rational. So the first we see that a rational number, the decimal expansion of a rational number is terminating or non-terminating recurring. Now we see the converse of that. a number whose decimal expansion is non-terminating recurring is rational. Now we can discuss the decimal expansion of irrational numbers. You know that the irrational numbers are root 2, root 3, root 5, pi, etc. What is the decimal expansion of these irrational numbers? Let us see here root 2. The value of root 2 is 1.41421, etc. And pi value is 3.1415925, etc. When you observe these decimal expansions, can you identify any pattern? Is there any number, any digit is repeating? No. It's a non-terminating and non-recurring. It's not ending and it's not repeating. So the decimal expansion of irrational number is non-terminating, non-recurring. Non-terminating, non-recurring. Decimal expansion is not ending and it's not repeating. It's going on like this continuously. Any digit, now you can see that the digits are repeating. Such numbers are called non-terminating, non-recurring. So the decimal expansion of irrational number is always non-terminating and non-recurring. So the converse also we can say that a number whose decimal expansion is non-terminating and non-recurring is irrational number. So we can conclude that first we discuss about the rational numbers. So that number whose decimal expansion is terminating or non-terminating recurring is rational. However, a number whose decimal expansion is non-terminating, non-recurring is irrational number. Now we can do one problem. Find an irrational number between 1 by 7 and 2 by 7. Irrational number between 1 by 7 and 2 by 7. You know that 1 by 7 is a rational number and 2 by 7 is also a rational number. The decimal expansion of 1 by 7, we see that is equal to 0.14285, etc. This block of digits are repeating that we see. And 1 by 7 is this much. Then what about 2 by 7? Very easily we can find out 2 by 7 because 2 into 1 by 7 is 2 by 7. We know the value of 1 by 7. Multiply by 2, you will get 2 by 7. So if you multiply by 2, 2 sevens are 14, 1 is remainder, 2 fives are 10, 10 plus 1, 11, 1 is carry over, 2 eights are 16, 16 plus 1, 17, 1 is carry over, 2 twos are 4 plus 1, 5, 2 fours are 8, 1 2 is 2. So you are getting 0.285714 bar. So that is the value of 2 by 7. We want to find an irrational number between these two numbers. To find an irrational number between 1 by 7 and 2 by 7, first we want to find a number which is whose decimal expansion is non-terminating, non-recurring, lying between these. You can find out many numbers like this. Infinitely many rational numbers you can write between these two. For example, here the decimal expansion is 0.14, etc. Here in second case it is 0.28, etc. So between these two we can find a lot of numbers. For example, that number should be greater than 0.14 and it should be smaller than 0.2. So many numbers you can write it 0.1501001001 10111 etc. Here this number between this number is greater than this, but it is smaller than this, and you can see that there is non-terminating, non-recurring. The digits are not repeating. Same way you can write another example, 0.1782101032 etc. Any number you can write it in this way. So these all are non-terminating and non-recurring. Another example you can write 0.2010111035 etc. That's also smaller than this number. So here 0.28, but here 0.2010 like that. If they are also not, and that block of digits are not repeating, so it is a non-terminating, non-recurring. So infinitely many numbers you can write between these two rational numbers. So dear students, I hope you understand this section. So today you should read your textbook, then complete your notes. First you should write the heading, real numbers and the decimal expansion. Then you should read the textbook and complete the notes. You should write your own notes. So after that heading, you have to write the main points. When you are reading the textbook, you will understand which are the main points you have. That means the decimal expansion of rational number, what we discussed, that you should write, and decimal expansion of irrational number. The decimal expansion of rational number is terminating or non-terminating recurring. Moreover, the number whose decimal expansion is terminating and non-terminating is rational. That point only you have to write. So you can look at the summary part of the chapter, the points 3 and 4. There are so many points are given in that points 3 and point 4, that you should write it in the notebook with the example. Then you have to write the questions what we discuss in this class. That means the questions like show that the number is can be expressed in the form of p by q, like that. 3 questions we done it in this section. So that 3 questions you should write it in your notebook. Afterwards, you have to write the worksheet. Today's your worksheet is exercise 1.3 full. So write neatly, write the question first, then answer. After each question, draw a line, then write the next question. You should draw the margin and you should put question number, write neatly. And study properly. Write and study these questions. Thank you.